today we are going to discuss the most important problem as far as a chemist is concerned, that is the problem of the hydrogen atom. So, if you think of the hydrogen atom, it is very clear that there are two particles, one is the nucleus and the other is the electron, and therefore, if you wrote the Hamiltonian for the system, how would it look like? Well, the Hamiltonian for the system will have kinetic energy of the nucleus. The nucleus is moving definitely, so it will have the kinetic energy of the nucleus. Of course, when I say kinetic energy, there is going to be an operator as far as quantum mechanics is concerned. So, that is going to have minus h cross square divided by 2 times the mass. That is what happens with the Hamiltonian all the time. So, if you have the nucleus, the mass may be capital M, right, and then there is the nuclear kinetic energy operator. So, that you will have to write as del square, but you should remember that this differentiation involves differentiation with respect to the position coordinates of the nucleus, right. That is what will happen. I mean, if we have two particles in a system, both will have kinetic energy, and when you switch over to quantum mechanics, from each one you are going to get a del square because it has kinetic energy. So, the del square that is going to occur here is going to be del square, and I will say subscript n to indicate that it is coming from the nucleus. And then you will have the electron minus h cross square divided by 2 small m. Why small m? Because now I am concerned with the electron, okay, and I will have a del square, but this will come from this del square will have differentiation with respect to the coordinates of the electron, 3 coordinates. So, del E square, right. So, nuclear kinetic energy operator, electronic kinetic energy operator, and then in addition to this you would have interaction between the nucleus and the electron. How is that interaction? It is Coulombic interaction. The interaction energy will depend only upon the distance between the nucleus and the electron. So, if the way we are proceeding, we are saying we have the nucleus which is rather massive, and then you have the electron, and what we are saying is that this has a mass m, this has a mass small m, and this is located at xn yn zn. That is what we are actually saying. Nucleus is located at this location, while the electron is located at xc ye ze, right. That is this is the these are the coordinates that we are using, fine. And then what will happen, the distance between the two, how will you write it? Well, we will have to adopt some shorthand notation because it is difficult to write xn, yn, zn and xc, ye, zd. So, therefore, what I will do is I will use the position vector. Position vector actually may be written as Rn. That is just a shorthand notation which says that this is equivalent to Rn. The components of Rn are xn, yn, zn. I mean, this is just convenience. I could have written xn, yn, zn, but it would have been difficult to keep on writing it again and again. And similarly, the position coordinate of the electron would be denoted as Re. This essentially means that you see I have some coordinate system somewhere here. With respect to this coordinate origin, this vector is Rn. That is the electron, and this position vector is Re. That is all. Fine. And if you wanted the distance between these two, how will you write the distance in terms of these vectors? Well, the distance is actually R e, vector R e minus vector R n. What is this? This is the vector that will connect the nucleus to the electron. It is this vector, and its magnitude will give me the distance between the two particles. That is all, correct. So, therefore, the interaction energy will be actually equal to, how much will be the interaction energy? The nucleus has a plus E charge, because I am assuming that it is a proton, and the electron has a, I mean I should not be putting the plus E here, but it is at the nucleus. So, therefore, the nucleus has a plus E charge and the electron has a charge which is equal to minus E. If I am saying that my nucleus is a proton, but the way the treatment is done, actually you can have 2 positive charges on the nucleus or 3 positive charges on the nucleus, but only 1 electron. So, if you say you have 2 positive charges, this actually will correspond to helium ion. If you say there are 3 positive charges, it will correspond to lithium 2 plus dipositive ion. But to keep things simple, I shall only be considering the hydrogen atom, but the same derivation everything will actually go through even if you had helium ion or lithium 2 plus ion. So, the interaction potential energy, if you say this is positive E plus E and if that is minus E, then the interaction energy will depend upon the product of these two. So, therefore, you are going to have minus E square, right, minus E square divided by 4 pi epsilon 0. This is happening because you are using SI units, 4 pi epsilon 0, and the distance R e minus R n. So, this is the full Hamiltonian for the system. Both the particles are accounted for. So, what will happen? I would have a wave function which will depend upon the coordinates of all the coordinates of the two particles. So, the wave function is going to be a function of how many variables? It is going to be a function of 6 variables. I am thinking of the time independent wave function, not the time dependent one. Why? Because I am thinking of the stationary states of the system. So, I want to solve the equation S I is equal to E psi, and here you have 6 variables which I may denote as R n and R e. Now, you see we have difficulties even in solving ordinary differential equations, and so if you say that you have a partial differential equation involving 6 variables, it seems extremely difficult to solve, correct. This equation seems extremely difficult to solve, but then you see if a problem mathematically appears difficult, what one should do is one should think of the physical situation. From the physical situation, you may be able to say something about the nature of the solution, and once you have some idea about the nature of the solution, then you may be able to actually find a way of showing that that is a solution. So, let us look at this physically. I mean, after all, what is this system? It is a nucleus, proton actually in this case, and an electron, and we know that this proton and the electron, what do? They usually form the hydrogen atom, even though you are saying there are 2 particles. So, actually what happens is that they form a hydrogen atom, and then if you think of the hydrogen atom, what can the hydrogen atom do? I mean, if you had hydrogen atom in this room, it can execute translational motion. What is translational motion? Translational motion in which there is no relative motion, right. Translational motion means the relative motion of the electron with respect to the nucleus is not important at all. What you have is a system comprising of the electron and the nucleus both travelling together as one entity. So, therefore, what I would expect, this is the Schrodinger equation, but physically what I expect is that this should describe definitely the translational motion of the whole thing. In addition to that, okay, it is possible also for the electron to move with respect to the nucleus, that is a relative motion, the distance of the electron from the nucleus can change. That is something that I can refer to as relative motion, motion of the electron relative to the nucleus, and that is what is actually more interesting for the chemist. Translation motion we understand, I mean there is nothing great about translation motion. So, the translation motion is motion as a whole, and what will happen, that translational motion of course will have only kinetic energy, but the relative motion is the one that is of interest, but both are actually contained in here in this equation. And so, I have to get out this translational motion and then look at the internal motion. I have to get rid of the translational motion. How would I do that is the question. Fine. So, how will you describe translational motion of the hydrogen atom as a whole? See, when you say translation motion, actually what you are saying is that the center of mass of the system is moving. Translation motion is motion in which center of mass is moving, and when you say the relative motion, actually then in that case the position of the electron with respect to the nucleus is changing. So, effectively that means Re minus Rn is changing, right. So, therefore, what I will do is I will change over to what are known as center of mass coordinates and relative coordinates. Why? If I had center of mass coordinates, what will happen, that will be the best for the description of translational motion, and relative coordinate will be best for the description of the motion of the electron with respect to the nucleus. Okay. So, how will you define the center of mass of the system is the first question that you would have. So, I have an electron which is located at Re, and I have a nucleus which is located at Rn. Fine. Now, this has a mass which we denote as capital M, that is the mass of the nucleus, and this has a mass which we denote as a small m. So, where will be the center of mass of the system? The way you would define center of mass is you would multiply Rn by the mass of that particle which is capital M, you will multiply Re by the mass of that particle which is small m, and then add the two together and divide it by the total mass of the system. This is the center of mass of the system, right. I mean you can think about it if you like. You see, suppose if the nucleus was very heavy, then the center of mass will be very close to the nucleus because the electron is very light. Okay. So, this one is one of our new variables, and what do I want to call it? I will denote it by the symbol capital R. Capital R will stand for capital X, capital Y, and capital Z. Do not confuse this with the coordinate system, coordinate axis, right. This is capital R is a vector. What is it? I mean it is very physical. You have a coordinate origin. Here is your hydrogen atom. You want to specify the center of mass of the hydrogen atom. So, you have to use a vector which is denoted by the symbol R, and its components you denote by capital X, capital Y, capital Z. Why did I use capital letters? Because R itself is capital, so its components it is better that I use capital letters. Then I want to describe relative motion. How will I do that? Relative motion is easy. All that I need to do is, you see, Re minus Rn is changing, correct. Relative motion means Re minus Rn, that vector, I mean the electron is going away from the nucleus, or the distance between the two is changing. So, therefore, this is my new coordinate which I will denote by the symbol small r, and the components of that vector I will denote as X, Y, and Z. These are the components. Okay. Now we have a not very difficult, I mean somewhat easy changeover. Changeover means, I mean, see here differentiation is with respect to nuclear coordinates and electronic coordinates. Differentiations are not with respect to capital X, capital Y or capital Z, but what I want to do is I want to write down the Hamiltonian in terms of r and small r. I do not want these Rn and Re, because for reasons that I have already told you. I want to describe the center of mass motion of the system as a whole. If I want to do that, I should express everything in terms of capital R, which stands for center of mass motion, and in terms of small r, which represents relative motion. So this Hamiltonian, which is expressed in terms of nuclear and electronic coordinate, you have to change over to center of mass and relative coordinate. So how will you do that is the question. Okay, I will do that. It is not difficult, as I told you. The way I am going to proceed is, so you see this Hamiltonian, let me rewrite it, minus h cross square by 2m. It would have dou square upon dou xn, what is my notation, xn square. So that is this part, and then what happens is minus h cross square by 2 m e, oh no, there is no e there, m dou square upon dou x e square plus dou square upon dou y e square plus dou square upon dou z d square. That is the kinetic energy, and then of course you would have minus e square divided by 4 pi epsilon 0 r e minus r n. Correct. So this has differentiation with respect to x n, y n, z n, x e, y e, z d. But I said I am not going to use those coordinates anymore. I am going to change over to another system of variables, which are capital X, capital Y, capital Z, and small x, small y, small z. This is what I want to do. As far as the potential energy part is concerned, it is pretty straightforward, because Re minus Rn is my new variable, right. Re minus Rn is actually R, and that is just x, y, z. So therefore this is actually nothing but R, magnitude of R, very easy, that part is straightforward. But I have to find out what this operator is, the kinetic energy operator is in terms of the new coordinates. But then without doing any calculation, again I will actually do the calculation because I want you to be convinced, but without doing the calculation, can we guess what is going to be the answer? See, I told you the physical reasoning. I have the hydrogen atom. What can it do? It can execute translational motion as a whole. So therefore it will have translational kinetic energy, and what will be the operator corresponding to that? Definitely you will have minus h cross square, right. Translational motion, the center of mass is the thing that is moving. So therefore you will have a del square. What will that del square be? It will correspond to the center of mass motion, right. So it is going to be del square with respect to this r, right. So therefore I am going to have del square. Let me be very specific. I will put r there to indicate that this is del with respect to the center of mass coordinate. And what about the mass? What mass will you put in? Center of mass is moving, so effectively the whole system is moving, and therefore you will have to put in the mass of the whole system. So therefore you are going to have minus h cross square by 2 times capital M plus small m. right. Actually this is the answer. I mean one does not have to actually compute, it is possible to compute and I will do it, but even before I do that I tell you that I can guess this has to be the way it comes out. And then you look at the relative motion. What do you expect to happen with the relative motion? See, the electron and the nuclei are moving relative to one another. There must be kinetic energy because of that relative motion. So therefore, what I would expect is I would have del square, where this del is carried out with respect to that r. So maybe I will put a small r there to be very clear as to what is happening. And then I will have minus h cross square by 2. Now what mass will you put in here? Again you can have physical reasoning. See, what is a relative motion? Relative motion is motion in which you do not worry about center of mass motion. You can even say center of mass is not moving if you like. Relative motion involves motion of one particle with respect to the other and it does not involve any center of mass motion, right. So you can say in relative motion center of mass of the system does not move, right. It is motion such that the center of mass is unaffected effectively. So if you say that you have this nucleus and the electron, okay. Imagine, I mean you think of maybe the Bohr model where the electron is moving around the nucleus to have a physical picture. So if the electron is moving, and if the nucleus is just sitting there, then is that fine? Is that center of mass motion, sorry, is the center of mass not moving in that motion? It is moving if you think about it. If the electron was here and if the nucleus was stationary, then the center of mass of the system will be here. While if the electron has come here, right, then the center of mass would have been here, and therefore you see a situation where the nucleus is just held fixed and the electron is going around, that will involve some motion of the center of mass. So actually what should happen is that when the electron moves, the nucleus also should move a little bit so that the center of mass of the system does not change. That is how the motion actually takes place. So how will it do that? Well, the answer is actually extremely simple. See, imagine this is the nucleus and here is the electron. Actually in the case of the electron and the nucleus, the center of mass is very close to the nucleus, actually it is even inside the nucleus, but we will not worry about that. Well, it is probably not inside, I mean nucleus is too small to be the center of mass to be inside, but it is very close to the nucleus. So you can say, okay, center of mass is here, right. Now suppose this electron, it is going and it is moving, it has come here, and then what will happen? You want the center of mass to be still here. So how is that possible? The nucleus should have moved to a new position which is something like that, correct. Then only the center of mass will remain unchanged. So when the electron is going around, the nucleus actually also will be going around a little bit, not by a large extent, but it has to move a little. So therefore when I say relative motion, it involves motion of both the electron and the nucleus. So therefore the mass that I will have to put in has to depend upon both the mass of the nucleus as well as the mass of the electron. But then again if you look at this, you see it is the nucleus that is almost not moving while the electron is doing all the work. The electron actually goes around quite a bit, but the nucleus because it is heavy, it does not move much, correct. So if you work out the algebra, what happens is that you will get here some effective mass of the system which you would be familiar. This effective mass is known as the reduced mass of the system. So why is it that you have reduced mass occurring there? Because both the electron and the nuclei are involved in the motion. they are both involved, but the nucleus moves only a little bit while the electron moves a lot, okay, such that the center of mass of the system does not change. So, this will be your kinetic energy operator, and then what will happen, you have minus E square divided by 4 pi epsilon 0 r, where that will represent the potential energy of the system. So, this is the actual answer that I shall get physically. I mean, this is quite interesting, because you see in most problems or in many problems, you look at the system physically, you understand it, and then you can say, without actually doing the mathematics, many a times you can say what is going to happen, how the solution should look like, many a times. If that is not obvious or you cannot guess it, then usually the problem, I would say, will deserve a Nobel Prize if you solve it. I mean, things which are not obvious, and if you find a solution, then I mean, it is difficult, it is not so easy, but in many of these problems, in a large number of problems, actually you can look at the situation physically and you can get some idea of the solution, and then look for a solution which satisfies that idea, and that usually works. Okay. Now, how will I do this? You see, the way I am going to do this is, I have dou square upon dou x n square, and I also have here, I mean, I have this, I also have dou square upon dou x c square, correct. And similarly, of course, I have the y term and the z term. I will consider them, but let just look at these two terms. So, this term is occurring with 1 by 2, sorry, no, minus h cross square by 2 m, while this is occurring with minus h cross square by 2 small m. Now, we have defined new coordinates capital X and small x. What is the definition of capital X? What is the definition of small x? It can be easily inferred from this definition. This is actually the vector. All that you have to do is, you have to think of the x component of capital R and the x component of this small r. So, if you think of the x component of capital R, what is the expression? It is going to be capital M into x n plus small m into x c divided by capital M plus small m, right. That is capital X. What is a small x? It is going to be x e minus, where is it? See, small x is the x component of this vector. So, all that you need to do is, you take the x component of the right hand side. X component of R e is x e and x component of R n is x n. So, therefore, it is going to be x e minus x n. Fine. So, let us now calculate, when I need to have dou by dou x. No, that is not what I want. I want to have dou by dou x n. Why do I want that? Because you see, I want to express, here I have a partial differentiation with respect to x n 2 times. So, I want to express this in terms of partial differentiation with respect to capital X and small x. So, if you ask a mathematician, he will give you this expression dou by dou x n, you can write in terms of these variables, which will be dou x by dou x n, okay. Let me be very clear. See, the original variables were x n and x e. So, partial differentiation with respect to x n means that I am keeping x e constant. So, therefore, I will have kept x e constant, and then I will have dou by dou x plus I would have dou x by dou x n with x e being kept constant into dou by dou x. So, this is what the mathematician will tell you. See, this is his rule for changing variables as far as partial derivatives are concerned. So, the first question is, what is this? What does it say? You have to keep x e constant, differentiate capital X with respect to x n, that is what it says. So, where is my expression for capital X? Here is capital X, you have to keep x e constant. So, this time is going to be kept constant, you have to differentiate with respect to x n. So, what is the answer? This is going to be kept constant, you are differentiating with respect to x n. So, the answer is capital M divided by capital M plus small m. So, this is actually equal to capital M divided by capital M plus small m into dou by dou x. What is the next term? See here dou x by dou x n. So, this is to be differentiated with respect to x n, keeping x e constant. So, answer is minus 1. So, therefore, you will get minus dou by dou x. Is that fine? So, dou by dou x n is just that. Similarly, I should express dou by dou x e in a similar fashion. Let me try to do that. Dou by dou x e is equal to dou x by dou x e, this is partial differentiation with respect to x e, keeping x n fixed, into dou by dou x plus dou x by x e, keeping x n fixed, into dou by dou x. Fine. And what is this object? Dou by dou capital X by dou x e, I will have to differentiate capital X with respect to x e, keeping x n constant. So, the answer is actually m divided by capital M plus small m into dou by dou x plus, what is the derivative there? This derivative, if you evaluate, you will find that the answer is unity. So, therefore, you will get dou by dou x. Fine. And now, to get this, what should I do? I will have to look at this expression. To get this expression, what I will have to do is, I will have to take the square of this. Okay. I will have to take the square of it, divide it by 2m and multiply by minus h cross square. And to get this, I will have to take the square of this expression, divided by 2 times small m and multiply by minus h cross square. So, let me just do that and look at the answer. So, this will become minus h cross square divided by 2m capital M divided by capital M plus small m, dou by dou x minus dou by dou small x, the whole square, that is one term, and the other term is minus h cross square by 2 small m. I can remove this, this is going to be put there, small m by capital M plus small m, dou by dou x plus dou by dou x the whole square. So, this is your kinetic energy operator, just the, when I say kinetic energy operator, the only the part from x coordinates are there. Well, you should also notice that there is a negative sign here while there is a positive sign here. So, when you take the square, what is going to happen? If you look at the expression, you will see that the negative term from here and the positive term from there. Because of that, there will be some cancellation. Okay. So, let me write the expression. It is going to be minus h cross square divided by 2 m square of this, if you evaluate, m square divided by capital M plus small m the whole square dou square upon dou x square. That is term number 1 coming from the square of this. Then coming from the square of that, you would have minus h cross square divided by 2 m dou square upon dou x square. Okay. There is a cross term coming from these two, but as I told you, there is a cross term from there, and if you do the calculation, you will see that the two cancel each other nicely. Okay. So, let me write the remaining terms. From here you will get minus h cross square by 2 small m m square divided by capital M plus small m the whole square, this right dou square upon dou x square, plus the last term will be dou square upon, well, minus h cross square divided by 2 m dou square upon dou x square. So, that is the, there is a cross term involving the dou by dou x and dou by dou capital X, the two together, but that will be cancelled by the same kind of term from the other side. So, what is the net answer? Well, it involves dou square upon dou capital X square and dou square upon dou small x square. So, as far as this term is concerned, you will have minus h cross square, see, minus h cross square by 2 capital M and h cross square by 2 times small m. So, the terms involving dou square upon dou x square are just these, fine. You have 1 by capital M here and you have 1 by small m there, correct. And what are the terms involving dou square upon dou x square? The first term is this one, and that you can look at it, it is actually equal to minus h cross square, well, maybe I should write it here, minus h cross square divided by 2 capital M is there, but there is an m square in the numerator. So, you are going to get capital M divided by capital M plus small m the whole square. That is the first term. What about the second term? Coming from here, it is similar, and it is going to be small m divided by capital M plus small m the whole square. So, this is what happens, right. See, what has happened is, where is it? Yeah, there is an m square, there is an m square, that m square and this m will cancel. So, you will be left with an m, and that m is the one that is occurring there, and that will be divided by capital M plus small m the whole square. So, what is the answer that you are going to get? Well, the answer is extremely simple. It is just what we had written physically. You get minus h cross square, this may be combined, you will get capital M plus small m. There is a capital M plus small m the square in the denominator. So, effectively this will become capital M plus small m into 2. There is a 2 that I have missed out. So, there is a 2 here. So, here again you will get a 2. Then this term will be minus h cross square divided by 2 into 1 by capital M plus 1 by small m, right, dou square upon dou x square, right. Now, you look at this expression, this is physically very meaningful. If the particle is very massive, then it does not move much, as I told you, nucleus does not move much, and therefore, the kinetic energy corresponding to its motion will be very small if m is very large. You have 1 by capital M. So, the more massive the particle is, you see it makes less contribution to this relative motion. That is what this equation says, right. We have already seen the physical reason for that. So, therefore, if I now say okay, I am going to define an effective mass, how will I define an effective mass? This whole thing, let me say, is equal to 1 by mu. This sum, if it is equal to 1 by mu, it will have the nice appearance. What will be the nice appearance? The nice appearance will be minus h cross square divided by 2 mu into dou square upon dou x square, where what is the definition of mu? I have defined it in such a fashion that 1 by mu is equal to 1 by m plus 1 by small m. This is known as the reduced mass of the system. Okay. Well, I had been a little bit careless here because I should not have forgotten to put the dou square upon dou capital X square, right. That is the kinetic energy operator will be there. So, here I have demonstrated this for just x motion. You can do exactly the same thing for y motion as well as z motion, and therefore, what will happen? You will have this Hamiltonian, right. The Hamiltonian would be actually equal to this. So, you see this Hamiltonian that I had, which was written in terms of the coordinates of the particles, that was not very convenient, but I have changed over to center of mass and relative coordinates, and then I find that the Hamiltonian has this form. Now, this is quite convenient. Why do I say that? Well, first of all, we have written it using our physical intuition. The second thing is, if you look at the potential energy of the system, okay, potential energy depends only upon relative coordinates, right. So, therefore, if you look at this Hamiltonian operator, you will see that this part depends only upon relative motion, while this part is the one that describes translational motion. And what does it say? It says that there is just kinetic energy due to translational motion. That is what this term actually tells you, while the other term has of course kinetic as well as potential energy terms, because it is a relative motion. So, if you had such a Hamiltonian and if you wanted to solve the Schrodinger equation, what will you do? You will say that H psi is equal to E psi is the equation that I want to solve. But what I will then do is I will say that the psi, which is the wave function, may be written as psi center of mass, right, a psi that describes the center of mass. This is essentially the method of separation of variables. Remember, our psi, the wave function, will depend upon all the 6 coordinates, right. And then we physically said that okay, there is center of mass motion, there is a relative motion, and we were able to use that idea to write the Hamiltonian as a sum of 2 separate Hamiltonians in a sense. The first term is the kinetic energy of center of mass motion, and the second term is the relative motion. So, this is Hamiltonian for relative for center of mass motion, that is Hamiltonian for relative motion. So, we were able to write the original Hamiltonian as sum of essentially 2 separate Hamiltonians, and therefore, what I expect to happen is that my wave function also should be possible to do a similar thing. My wave function must be a product of the center of mass motion and relative motion. So, therefore, this psi center of mass will be a function of r, and then I would have psi relative, which will be a function of small r. So, this is essentially the method of separation of variables, and what will I do? I will take this assumption for this ansatz, put it into the Schrodinger equation, and use the method of separation of variables, and then you will find that the equation can be nicely separated. I will do it in the next lecture. It can be nicely separated into 2 separate equations. One will describe the center of mass of motion as a whole, and the other will describe relative motion of the electron with respect to the nucleus. And then center of mass motion is very easy. It is just a free particle moving in space, right, very easy. And the other one is a little bit more difficult, because it involves the motion of the electron with respect to the nucleus, and I will tell you how to solve it. Eventually, it will give me the atomic orbitals eventually. Okay. So, thank you for listening.